Hi everyone, this is Mr. Bowman. We have finally finished Chapter 2 on polynomials and rational functions, and we're going to move on to Chapter 3, which is exponential and logarithmic functions. Both of those are topics that you would have covered in previous classes, Algebra 1 and Algebra 2. So hopefully you find this a review. If you're having any difficulty with this stuff, particularly the initial stuff here, make sure you touch base with your teacher right away and get some help on it because we're going to move pretty quickly. So exponential functions have a very specific form. They are of this form right here. F of x is equal to a times b to the x, where a and b are both real numbers, but they have specific restrictions on them. A cannot be 0, B needs to be positive, and B cannot be equal to 1. When talking about exponential functions, we often refer to A as the initial value of the function. That's because very often this is used in modeling and the initial value occurs at time 0. It is also known as the y-intercept of the function. So in other words, if you plug in 0 for x, you're going to get a times b to the 0, and with the restrictions on b to the 0 is going to be 1. So f of 0 is equal to a, or the initial value. B is called the base of the exponential function, and from the base you can determine the rate of growth or decay, which we will talk about more later. So one of the things you have to be able to do is to recognize whether or not a function is an exponential function, and very often students get confused by that. The one thing I like to remind people is that the variable is in the exponent. You have to have an a value, you have to have a b value. A cannot be 0. B has to be positive and not equal to 1. So sometimes when you get a function, it's not in that standard form. You can manipulate it a bit and put it into that standard form and figure out the values for a and b and then determine that it is an exponential function. So for example, the first one, 3 to the x could be written as 1 times 3 to the x, in which case a is equal to 1 and b is equal to 3. So the answer is yes, this is an exponential function. Number 2, 6x to the negative 4 could also be written as 6 times 1 over x to the 4th power, property of exponents. Well, if you look at that one, you would have an a value of 1, but your exponent is a constant, and in an exponential function, the exponent has to be the variable, and your base would be a variable in this example, so this is not an exponential function. Number 3, a is equal to negative 2, b is equal to 1.5, and a is not 0, b is positive and not equal to 1. So yes, this is also an exponential function. The next one, a little bit tricky. 7 times 2 to the negative x could be written as 7 times 1/2 to the positive x. Again, property of exponents. So in this case, you can see that a is equal to 7 and b is equal to 1/2, and we meet the requirements for an exponential function. Number 5, really tricky. We've got to figure out if we can write this in the a times b to the x form. Well, the square root of 7 to the x is the same thing as 7 to the x raised to the 1/2 power, okay, which can now be written as 7 to the x over 2, because when you raise a power to a power, you multiply the exponents, which could be then written as 7 to the 1/2 raised to the x power. basically what we did is we switched the locations of the exponents, the 1/2 and the x, which could then be written as the square root of 7 to the x, which could be then written as 1 times the square root of 7 to the x. So a is equal to 1, b is equal to the square root of 7, and we've met the requirements for an exponential function. That one often throws people. And then finally, number 6, it looks like it's in exponential form, but the variable is not really a variable. Pi is not a variable. So this is not an exponential function. So as I mentioned at the beginning of this video, there are some things that we're going to go through pretty quickly in this chapter. And one of the things that you just witnessed was properties of exponents. So again, if you're struggling with some of those examples that I did up there because of not fully understanding properties of exponents, make sure you ask your teacher quickly. All right, the next thing we want to do is we want to evaluate an exponential function using function notation. Again, this exponential function, it's implied that the initial value is 1, so 1 times 2 to the x. So evaluating f of 2 simply means that we are going to find 1 times 2 to the second, which is going to be 4. Evaluating f of 0, well, f of 0 is the y-intercept, or the initial value, so 1 times 2 to the 0 power, which is 1 times 1, which is 1. F of negative 3, 1 times 2 to the negative 3, well, that's the same as 1 times 1 over 2 to the third power, which is 1/8. F of 1/2, 1 times 2 to the 1/2 power, or the square root of 2. And then finally, f of negative 3/2 would be 1 times 2 to the negative 3/2, and we're going to rewrite this as 1 times 1/2, or 1 over 2 to the 3/2. So that 3/2 only goes on the denominator there, which is going to be 1 times 1 over 2 root 2, or 1 over 2 root 2. Again, I can't remind you enough, if you're struggling with properties of exponents or properties of radicals, some of that stuff that I just simplified there, make sure you ask your teacher about it. So to move on, we want to talk about exponential growth and decay. Exponential growth occurs when in your function, your exponential function, a times b to the x, b is greater than 1. So basically you're constant, as x is increasing, you're multiplying by a bigger and bigger number, so your function value or your y value is increasing. An example of that would be f of x is equal to 3 times 1.4 to the x power. Exponential decay occurs when b is between 0 and 1, which means that as x is increasing, you are multiplying by a number smaller than 1 but bigger than 0, so y continues to decrease. An example of that would be g of x is equal to, let's make this one a little bit tricky, 1/3. Even though the base is not 1, that's okay. That does not determine whether or not it's growth or decay, times 1/2 to the x. It is the 1/2 that determines whether or not this function is exponential or growth or decay, not the 1/3. The 1/3 is just the initial value. So to recap, determining whether or not a function represents exponential growth or decay, it's based strictly on the value of the base. If the base is greater than 1, it's growth. If the base is between 0 and 1, it's decay. We are going to finish up this short lecture, video, whatever you'd like to call it, by looking at a really common problem. You're given a table of values which represents points on the graph of a function. or you're given points on the graph of a function and you are asked to find the function. And in this case, we are told that the two functions are exponential functions. So they will take the form a times b to the x. So when you're given that, if it's available, the first thing you should do is find the initial value, the y-intercept. So we're going to highlight that. And we recognize the y-intercept because the y-intercept always, always, always occurs at x equals 0. So look at the initial value. This is also called the y-intercept of the function. And so let's start with g of x. We're going to do this for two functions. G of x, or let's say g of 0, is equal to 4. So the y-intercept occurs at 0, 4. The y-intercept for g of x is 4. H of x, or h of 0 for the y-intercept, is 8. So the y-intercept for h occurs at 0, 8. That tells us what we often refer to as the initial value, the a value in the function. Once you've determined the initial value, the a value in the function, you're going to move on to find the b value in the function. So here's how you do that. We will do g of x first. And remember, g of x is going to be of the form a times b to the x. And we are going to plug in what we know the a value to be, 4 times b to the x, and pick an x value. If you can, pick an x value that's easy to deal with, or the easiest to deal with. And so we're going to pick 1, because that's going to be the easiest in this example. And so when x is 1, the value of g is 12. And now all we have to do is solve. So b is equal to 3. And our function, g of x, is equal to 4 times 3 to the x. And it wouldn't be a bad idea to go up to your table and verify that those numbers work. So 4 times 3 to the negative 2 should give you 4/9. 4 times 3 to the negative 1 should give you 4/3. 4 times 3 to the 0, and so on and so on and so on. However, if you're not given a simple point where x is equal to 1, you can still do this. So let's pick another set of values to plug in there. So let's pick, I'm going to highlight it in green, let's pick 2, 36. So when x is 2, g of x is 36. So we'll do another example here. So we've got our function. It's of the form 4 times b to the second, because when x is 2, g is 36. So we are going to divide both sides by 4 and get b squared is equal to 9. So when we solve this, we would get b is equal to plus or minus 3. But remember, the restrictions on b are that b has to be positive, so we ignore the negative 3. So b is equal to 3. And once again, we've determined that g of x is equal to 4 times 3 to the x. Essentially, what I'm trying to point out here is that it doesn't matter what point you use, as long as you use the initial value and one other point on the graph. So let's do h of x, or find h of x, using that approach, a times b to the x. And we're going to pick a point that's not so easy to work with. We know the initial value is 8. We don't know b. We're going to pick x is equal to 2. And when x is equal to 2, h of x is equal to 1/2. So we are going to divide both sides by 8. We get 1/16. And that's equal to b squared. If we were to take the square root of both sides, we would have plus or minus 1/4 is equal to b. But we throw out the negative because b has to be a positive number. So we know b is equal to positive 1/4. Therefore, our function h of x is equal to 8 times 1/4, 1/4 to the x. And that will work no matter what points you use other than the y-intercept. That is it for today. Have a great day. Talk to you soon.